So all of that work before, we have the Gibbs equations where you have all this thermodynamic works to relate two states of a system based on compressible flows. We know how to relate densities, pressures, and temperatures for two different states. And that's kind of where all of this gas dynamics stuff goes for undergrad stuff, is you just know state one and then state two based on the process. So you're trying to figure out a temperature or pressure. But we haven't talked about velocities yet at all, so there's not really any flow happening, right? Everything before was just involved with state one, state two. There was we invoked nothing about a velocity of a flow. So that's where we have to now invoke velocity somehow, and we have to invoke compressible flows, and that's this idea of the speed of sound. Okay, speed of sound from thermo. Right, let's go this way. That's where we're headed next. So we have to figure out the speed of sound value called C, and we have to get this value based on thermodynamic properties. Because what we want to do is we want to normalize all of our velocities by the speed of sound in a medium. Okay, pressure waves. So we want to figure out the speed of a wave, right? So there's transverse waves. And then we have longitudinal waves. Okay, these waves is like, right, if you have some person like this, and he has like a rope, and he's doing that thing where he flicks it like boom, 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 right? So that is something like this, right? So here would be a wave speed. We'll call that one C. Other ones is the surface of a water flopping around, right? Right? So you splash and the waves go out that way. This crest here is a transverse wave because the medium has gone up and down, so it's sort of a going out that way. Longitudinal waves is right. This is a slinky, right? So if you have a slinky, you hang it upside down and go whoop, right? So you just slinky, and it bunches up kind of here, and then it goes like there. You can follow that compression down the slinky medium. You can see it. So that's a longitudinal wave. And then the other example is if you speak, right? Like you have those little like air guns, right? There's a bunch of molecules of air, and then your sound wave has compressed the air in some little region. So these are molecules, etc. But the idea is like here is this compression wave of all the air molecules. You go bah, and you compress a little bit of you compress air in front of your mouth, and then because of that it moves backward because of Newton's second law, third law. So then that progresses throughout the media, and then that has a speed. Right? Even this thing had a speed as well, and all these are related somehow about how the wave information propagated forward in the media. So this idea is how we're going to be able to get some idea of how does a pressure wave propagate through a media, and the speed of sound is the fastest it can go, right? So pressure wave propagating through an air media, or actually any media, because what we can use, it's still the same properties. It's just dependent on these E's, right? It's dependent on the betas and K's and E's that we've done. So there was a reason to write out the E's, all I'm saying. But this is the wave we're going to talk about. Right, these pressure waves in your media, speed of sound. Okay, so how are we going to analyze these things? Well, we're going to do the same thing we've always done, and we're just going to draw the super simple picture, right? And then draw a control volume around it. So let's just say I have a control volume right around here's the compressed parts. And here's the less compressed part of air. Okay, these terrible pictures, but it is like not compressed, compressed part of the air. So behind it, pressure and a little bit of change in pressure, right? And we have change in densities, in changes in enthalpies, and then up front we can have the actual pressure. Boom. And then this control volume is propagating forward at the speed of sound that I don't know yet. So two things to consider is that this idea is we can follow, right? We can follow the wave, meaning that my control volume is moving along with the wave, or we can have a relative control volume where we just stay stationary with the volume and look at and consider things like that. So the relative one is the way to go, where you're just fixed along and you're riding along with the wave. So this would be the same thing if you did have a wave crest like this and you're a little surfer, right? And you're just at the very tip top of it. A moment later, you're still just with it, right? So this is relative. This is your coordinate system view just sitting on the wave itself moving. Okay. So then those control volume properties are the same here. You just now have to do that if you're moving, this is C, and then relative to the control volume, C minus a dV, a change in velocity. So before, the control volume is moving at C, but relative to it, it's minus C, and then this change in velocity. Okay, so in this control volume, first, right, we'll conserve mass. So think of flow rate in and out, right? The flow rate passing through has to equal to flow rate passing out because they're normal, right? Because of the normal vectors of this control surface. It's the same integral thing we've done at all term. Okay, but let's do this differentially now, which kind of helps for all this compressible stuff. Then you have A is still constant. And then here, right, the out going this way is the dV here. Okay, so if you multiply all these two things together and you use the fact that, right, all double differentials, so any term like this, neglect because it's two differential terms. Okay, so boom, boom, boom. So in this multiplication, clearly these two things will happen, so they'll cancel out. AC. C. And this is after, there's a fourth term, but it had a dP and a dV in it, so neglect it, throw it out. So that cancels out. And then you get the continuity expression that is a rho change in V, the A's cancel as well. That will equal a C rho. So that's just from conservation of mass. Okay, this relationship here. No involvement of pressure though yet, right? Haven't done any talk about pressure yet. So that's the conservation of momentum, or as I think of it, the work energy theorem. So second equation we need to relate this stuff as well. I conserve mass in and out. Now I need to conserve the flux of momentum, or I can think of it as the work energy theorem. So I know that the work I do must change the kinetic energy. And then you just get dx the whole time. Just write that down, remember it. Write that picture down too. Okay, so I don't know why I do this, but it just helps me. I know that the work I do has to equal the change in kinetic energy done for the system. So that'd be, right, all of these forces by a dx, or virtual work. Pressure times an area. Pressure plus dP, area, dx. So then the dx cancels. I never really had to do it, but I just see it like that. Where the dx is the width of the pressure thing. Okay, and then this is rho. Okay. This is the sum of the pressures. So I'm sorry. This is the work side because it's a force times this is the force. So this is work. This is just from here, you can cancel these out because these dx's cancel out. Hope that didn't confuse you too much. Cancellations occurs, right? And then you get the dp dv. This is a velocity, not a volume, by the way. And that's just canceling out. Again, if you see a combination or right, and sort of dx dv's. All right. And then one we had before, we had d. So these two together give us that P. Boom. That is the speed of sound squared is equal to change in pressure with change in density. Makes a little bit of sense because the change in pressure is related to, right? Change in the pressure is related to like the change of the, right, the force happening. And this change in density, you can see that's related to it too, because in your control volume, there was more dense molecules in this control volume, so there had to be a change in density because over here, sort of, this density is less than this density. Right, this density out here, because the molecules are spread out, has to be less than the inside of the traveling wave because it's denser. Right, the molecules are all packed up in there. So it makes sense that there's a dp, that there's a d rho involved in there. And then with the d pressure, that's involved where you did apply some force to the media involved. So that is the change in pressures. Pressure is a force divided by an area, so it's sort of the field version of force. What else do we see? We also see that c squared, so it makes sense too because it's always a positive quantity, at least in the sense of this relative thing. You can have right, if you have direction, but this is speed, so speed should be squared. So we haven't even talked about ideal gas yet, though. So we have rho. Okay, so now we're going to invoke ideal gas laws to see what the speed of sound is, because sound is air. Because speed of sound, you're referring to how fast does a pressure wave travel through standard air properties. Okay, so speed of sound is related to when you say when you apply ideal gas. Right, you're applying ideal gas to the right-hand side of the equation. Okay, so what you don't use, you have to use the gamma term. So you don't use that, but you do, right, what it is, you say that this is something like this. You have to use the gamma expression, which is some sort of constant. This can be shown from those Gibbs equations. Okay, so just compute this thing now with this relationship, and then you'll get pretty cool. So speed of sound for an ideal gas of air is 1.4 times r then t. Okay. Importantly, this looks like about 50 square root t for imperial units. Units. Okay, or it looks around like 340 meters per second at 15 degrees. So at 15 degrees, and then it really looks like for SI units of meters per second. So this is feet per second, this is meters per second. But for the speed of sound is dependent on temperature, and you see that from the ideal gas law. So just go 50 square with your temperature. You can quickly figure out how fast it's going in there. Pretty cool, right? I mean, you have to do a lot of work to essentially, right? You have to do a lot. You could have done everything before, right? You could have done the last part of this lecture to just derive this expression here, but you couldn't have gotten anywhere. You couldn't have gotten to the temperature thing if you didn't use all the thermodynamics, because to get this relationship, you had to use the Gibbs equations and those isentropic properties as well. Okay, so that's just for the speed of air. So for air, you could use the ideal gas law, right? But in most generally though, the speed of sound through any media, as we see, right, is the same derivative with a constant entropy. So that's the most general term. So what's the speed of sound through metal, or what's the speed of sound through a liquid? Well, you can't use this expression because this limits to 0 for a solid or a liquid, right? Right, so you could also do this expression, make it look like that. This is the coefficient of compressibility. And that's because, right, remember that relationship we did before, it looked like this. Right, that's what we had before, this constant, right, this coefficient is inherent to a media, and it's defined by this. So it's just substitution, you get that the C is 1 over rho to the K. Okay. But the problem is, for a solid or liquid, this is kind of harder to measure. We don't really have a way to actually measure this thing because it's just so enormously small. So the problem is, if you're using this K to figure out what C is for a solid or liquid, or it's right the speed of a pressure wave in a solid media or a liquid media, it blows up to infinity because this expression is going to 0. So that's bad. But for the solid or liquid, right, we do get this expression we had before, which is just a better lens to view this idea out of. Okay, so while the E for some reason is easier to measure, so then for a solid, right, we do know this went away, so then my K actually just looks like 1 over E, modulus elasticity. So you just used E then, right? So then for a solid or liquid. So for solid liquid, the speed of the wave propagation in that media is proportional to this, where you have a modulus of elasticity and the density of it. And now you can usually calculate these things, right? So then C, it's about 14 for water. And then steel. Right? So in water, it's definitely a lot faster. It's like, what is that? It's like 4 times faster in water than it is in a gas. And then for steel, it's just enormous, right? So pressure waves in meteor, compression waves in solid materials, they're really stiff. And that's the idea. When they did the gravitational waves or something like that, it was enormous. That's the conclusion, that like space is super stiff. It's one of these types of relationships here. Okay, so that's all this work now on these values of C. Most importantly, having that the velocity of sound is 340. So that means that the pressure wave So most importantly, we have now a thermodynamic limit, or some value of velocity that's just very important for gases. It's the speed at which any pressure, any wave can propagate forward, right? 340 meters per second. Some T dependent, so this is at 15 Celsius, okay? But this is how we then define a Mach number, right? Mach numbers are the speed that you're, right, sort of that U infinity, right, normalized by the C. So remember that external flow situation? It's a terrible foil. So something like that, that U infinity, right? Here's the issue, right? This is the idea that if it's going so fast that you approach this actual value, something's happening and something's going to change, right? And that's this Mach number that we get to. And you'll see many relationships spawn from it. But we did a lot of work to, right, get it, like the idea of compressibilities, right? This idea of what does it really mean for rho, right? What does it really mean now for pressures, right? So for my pressures to vary with rho and now temperatures. So just analyzing this equation of state involved with flow state to state. But next lecture, we'll actually get to the flow properties of it. Everything till now was really just, right, the Gibbs equations, which relate pressures and temperatures, but there's no process involved in there for flow, velocities. So that is where we define this Mach number, and then we'll get into isentropic flow, which is the easiest case for compressible flow. But we needed all those Gibbs relationships, or the isentropic relationships for flow, to do anything. And more importantly, is this limit is not bounded, right? So the idea is this Mach number can just be special, but we can make, planes and things that can have Machs of higher than 1. So, right, so there's some property here. If this is 1, something important happens, then you can go past that. So, right, now next lecture will be isentropic flow relationships. So we'll bring in the idea of flow. Okay, this number will help us bring in the idea of compressible flow. This lecture really was just talking about what does it mean to be compressible, and we derive these many relationships. But the next we'll talk about an actual flow problem, and that's really the fluid dynamics problems of it. This first was a course in thermo, but it helps to just see what does it mean to be compressible. Very non-intuitive question. And the idea being that here's a property. Okay, and there's a Mach number line, so Mach 1. So below you have subsonic, supersonic, and we have missiles now that go so fast that have a hypersonic regime now as well. Usually it's when you get past Mach 5. I think there's some missiles that get up to like Mach 7 now. And there's just a ton of there's even more physics that changes once you get that large, or you're getting towards like an order 10 number. Amazing. Very difficult stuff. Okay, so I've talked enough about thermodynamics. So next lecture, we'll talk about flow.